Good morning, everyone. Thanks for joining this joint talk between Binfan from Alluxio and K1 from Meta. In this lightning presentation, we're going to share you a set of interesting learnings by applying a set of optimizations on RaptorX to help us improve the performance, understanding, and also workload analysis in Presto. This is a joint work between Alluxio and Meta. Let's quickly introduce ourselves. I am Binfan from Alluxio, founding engineer and VP of open source in Alluxio. And K1, she is from Meta, and she's from Presto team in Meta. We have been working together in this collaboration for a year. So let's first go through what is RaptorX if you are not familiar with this project. RaptorX is basically a set of optimizations to help Presto building a hierarchical caching solution to deal with disaggregated storage. The set of optimizations include Alluxio data cache, Heavy metastore and file information metadata cache, and etc. This is open source collaboration between different companies and also across different communities. We have been working on RaptorX in past year or two, and the results we get is pretty impressive. This boosts the performance for interactive queries in Meta by 10x and has been deployed in production at tens of thousands Presto nodes in Meta for a year. If you want to understand more details for this work, you can refer to our talk or previous talk and previous blog. So in this presentation, we're going to focus on follow-up work on Presto. And this is one of the major work we're doing is building a shadow cache. Before we go to explain what is shadow cache, let's see how Kay is operating RaptorX in production. She needs to route the query traffic, the Presto traffic to different clusters. And she needs to make sure in each cluster, it has the information and the sufficient resource allocated to this cluster. So she is collecting the information, asking questions like, oh, do I have enough capacity in this RaptorX cluster? Or what is the potential impact to the cache efficiency if I route more workload there? So she is asking me questions like this from time to time and see how Alluxio data cache can help here. That's why we build a shadow cache, which is a lightweight plugin to Alluxio data cache at Presto to track the working set and collect information about the hit ratio. Let's go for some example. If K is asking me how much unique data is queried in the past 24 hours, the Alluxio shadow cache can return to K with information like, oh, in the past 24 hours, unique bytes accessed in this period of time is 850 gigabytes from this particular worker. Further, he may ask, say, if we have infinite amount of cache capacity, what is the hit ratio? And then just to compare as the baseline, then the Alluxio shadow cache can return answers like the estimated hit ratio, which is the upper bound, can be 98% if the cache is infinitely large to hold all the data requested in the past 24 hours. So such an algorithm, or you think it's plugin in Alluxio, we want to build this to be low memory overhead and low CPU overhead. And what's more, we want this to be online. We don't want to run some analytics afterwards to parse the offline logs. And this should be accurate enough to give us a bound error ratio. The solution to this is to use a setup or a chain of Bloom filters with each tracking the unique number of unique objects in one time window. As shown on the bottom right, you have 4 Bloom filters, each tracking objects in the past 6 hours. So in order to get this, with this setting, to track working set of 27 terabytes, only 125 megabytes memory is required in our initial implementation with only 3% error rate. And this prototype is available since Alluxio 2.7.0. There's some ongoing work to further improve Alluxio data cache, shadow cache. One is to explore the possibility to use a new and faster storage, emerging storage like a Intel Optim memory. How to track when this Optim memory is used for caching data. How we can track a magnitude more data if Optim memory is used. And also, how do we move the data structure from the on Java heap memory to off heap like an Optim memory with more accuracy or more information. And also, we want to support table level breakdown on the cache insights. Kay will talk about why this is a reason, why this is asked from Meta. And we are also working on some algorithmic optimizations to further reduce the estimation gap by integrate updates better with more advanced probabilistic data structures. I will turn this to Kay to talk about how Kay is really using this to solve her problem in Facebook.
Yeah, thanks, Bing. So next, I will talk about how we use shadow cache to solve the pain point we were facing. So first, the pain point is that we don't know how large the caching working set is. So we have limited flash storage on every Presto worker, and we want to understand if a cluster is bounded by the storage. Meaning if it is, then adding more storage is going to help with the cache hit rate and thus help with end-to-end query latency. If it isn't, then there's no need to do so. Secondly, shadow cache will also be helpful to explore and evaluate the potential improvements in the new caching algorithms. Right now, we are using plain LRU, but more sophisticated eviction policy could potentially bring up the cache hit rate or save some storage. Lastly, we want to optimize the routing algorithm for better balance and efficiency. I will explain a little bit more. So for the routing logic, we shard the cache among clusters based on table name, meaning every cluster has a set of tables to cache. And the query that accesses the same table will always go to the same target cluster to maximize its cache. So unfortunately, under such architecture, even though from storage perspective, the cache is evenly distributed, from the compute perspective, we will see imbalance when certain clusters are more overloaded in CPU than others. Next slide. So to solve this issue, we have several options for redesigning the routing logic. But all the solutions above need extra storage for cache. And that's where we need shadow cache to give us insight to do the trade-off. Next slide. Yeah. So here are the four main metrics we observe in the production. So we observe the real cache usage and the shadow cache working set. And we observe the real cache hit rate and also shadow cache hit rate. Based on the comparison of those four metrics, we will have this decision tree that helps us understand the current health of the caching system. So either this workload is not cache friendly at all, or the cache storage is under or overused. So to dive deeper into more granular cache insights, we are also collaborating on adding the table level breakdown to the shadow cache as well. Next slide. So lastly, I'm going to talk about another two enhancements we've added on RaptorX. The first one is the runtime stats. So it's an improvement in collecting and aggregating query level runtime stats on Presto engine to better understand the time breakdown. Because a lot of times during debugging, we want to understand why one particular query is slow, where is bottleneck at. So the runtime stats will give us breakdown on how much time is spent on metadata call, like the planning time and the scheduling time. Also on the worker, how much time is spent on reading from external storage and the cache. Furthermore, how much time for footer, row index, etc. Also on the feature level, we also add the stats on fragmented result caching, materialized view, and the per query level cache hit rate to better understand the performance for each feature. So this enhancement on the runtime stats has been merged and used internally. It has helped us understanding multiple areas of improvement. So feel free to use this feature if needed. The second one is the semantic aware caching, where instead of file level understanding, the cache would be smarter and understand the semantic meaning of each request. But this project is still being worked on, so stay tuned. Yeah, that's much about it for our session. Thanks everyone for tuning in.